classification in the last lecture. I'll sort of complete it. There are just 2-3 more lines to be written down or explained, and then we'll say something about the Brunson theorem. Okay. So I'll start with the theorem we had written down last time. We had proved it, so I'll not be proving it again. But I want to say how to finally characterize the irreducible unitary representations using them. So, by the irreducible unitary representation of L to R. And recall we used J pi for the K types that are appearing for pi restricted to K. So J pi is all those n such that eventually n is equal to 1. Right? So first one was J pi is even or odd type, right? Only same parity. If Q was the Casimir's value, right? Casimir acts like a scalar on irreducible representations, and if Q was not equal to n into n minus 2, so we should let's write the second case in bracket. So even odd Q is not equal to n into n minus 2 for any is this too small? So then I'll use both the boards for any n positive even, then J pi is doubly infinite. So as I had remarked, this corresponds to the principal series case and the complementary case. Okay. And the other case is when Q is B, J pi is even or odd, and Q equal to n into n minus 2 for any positive even or odd. Then we have three possibilities. One, J pi starts from n and goes to the right, n plus 2, n plus 4, etc. So this is the holomorphic discrete series. And 2, J pi goes to the negative side, left side from minus n onwards. Minus n, minus 2, minus n, minus 4, etc. So this is the anti-holomorphic discrete series. And 3 is when J pi is finite, which will not fall into the unitary irreducible category, but the admissible representation, the usual finite dimensional representation. J pi minus n plus 2 to n plus 2. Okay, so these are the finite dimensional cases. So remember we denoted this by dn plus, this was dn minus, and here we had two sets of principal series, phi lambda minus, this was the one we used for the non-trivial representation of M and unitary character of A, and we had the complementary series for maybe between 0 and 1 or something like that. Again, we should not be using any expression. So this is what we had so far. Now, how do we, if we start with a unitary irreducible representation phi, we want to say it is one of them, right? So let us, let's write down one more result just to make sure that we can actually complete the classification. So start with the definition, which you have already seen. If phi and phi prime are admissible representations, they are said to be infinitesimally equivalent if phi dk, so these are the k finite vectors for phi, and phi prime, so phi prime has a similar set of k finite vectors which I denote by dk prime. Yeah.
So the finite dimensional, those are not unitary, right?
Can you speak louder, please?
This third one, this finite dimensional list,
Ah.
those are not unitary. It is not.
They are not unitary. So this is actually so this will not be in the list. Okay. But when I classify admissible representation, this will be there, right? So yeah, so you can ignore that one. I know there are possibilities of J5, but we know that there are no finite dimensional representations, so this doesn't appear.
So this is the theory for SL2R, and is it easy to go from here to classifying irreducible representations of GL to R from here? Or maybe how do we go from SL to R to GL to R?
There is no GL to R in this course.
It's only you are taking a product with positive reals, so it should be.
There is disconnected group.
Okay, yeah.
But
GL2 plus
R is
not
It's not like GL to QP or so GL to R is not there.
So yeah, they are infinitesimally equivalent if the infinitesimal data are isomorphic, right? So that means are algebraically equivalent, which means there is a map. Okay, so that is there exists a linear isomorphism T from Pk to Pk prime such that also it should commute the actions, right? So T usual intertwining operators, okay? So T phi dot x equal to phi prime dot x. So they are infinitesimally equivalent, the infinitesimal data should be same. Okay, so easy corollary to whatever they have been doing so far is if phi and phi prime are irreducible and admissible, then they are infinitesimally equivalent if and only if the Casimir value q and q prime, so q is the Casimir value in phi and q prime is the corresponding value in the representation phi prime, they are equal, and j pi, the k pax intersection phi prime is not equal. Of course, they will be equal. Just a weird way of writing it. So proof is clear. I'll not bother about it. So T. So I'll just tell you how this is justified. T is an isomorphism between these two vector spaces, and T commutes with or T intertwines these two operators, or it will also intertwine the Casimir. So the Q values are same. Once the Q values are same and in the intercept, they have to be same, right? Because J pi has only those possibilities, right? And so if Q values are same, then these possibilities are also same, right? And if they intersect, they have to be the same. So then they are infinitesimally equal. Okay, so this is easy. So yeah, so the last result we need to complete the classification is whenever we have two representations such that they are infinitesimally equivalent, they are also unitarily equivalent. Okay. So to check if something is unitarily equivalent to the list we have, we just need to check the infinitesimal value. Okay, so this is the theorem from this state. I will not prove. Unitary irreducible. Reducible. Cell 2, which are infinitesimally. So we need to go only one direction. The other way is trivial, infinitesimally equivalent. Then phi and phi prime are unitarily equal. So there is a unitary map which intertwines the pi action and the pi prime action. Okay, so they are same representation. So to check, so now, well, I still have to do some computation, but mostly I will tell you the remaining things as a story. So, okay, so we have the list as well, right? So, stop here. So the list we have is the following. So we have pi lambda minus, right? For lambda in R. So this is the principal series. And among the principal series, this one is not irreducible when lambda is 0. Remember that. So pi 0 minus, right? It splits into 2. This was d 1 plus the next some d 1 minus. These were the limits of the discrete series, right? So this was let's say 1, 2. We have dn plus and dn minus for n greater than or equal to 2. This is the discrete series, and we have the complementary series Cu and 1 and the trivial. Right. So this is our list of irreducibles, or well, list of irreducibles which we had written down, and our aim is to say that these are all. Okay. Okay, so how do we go about this? To complete the classification, so start with the pi unitary irreducible. Okay. So I have the q value and I have j pi. Right. And I want to say it is one from the list. So let's take one case to argue, okay, because there are several cases, so I don't know what is j pi, right? So let's say j pi is, so I know that j pi has to be one of these, right? There are no other possibilities. So let's take the first one. So assume that j pi is even and doubly infinite. So my space V sub k is going to look like I have V0, direct sum V2, direct sum V4, etc., and to the left I have V minus 2, right? V minus 4, and so on. That's how the K-finite vectors are going to look like. Remember that all the Vn's are one-dimensional, okay, and they are all orthogonal to each other. So if I choose norm 1 vectors from each of them, I have an orthonormal basis for my Hilbert space. Okay, so it looks like simple. And recall all those operators we had x alpha and x minus alpha. So x alpha goes this way, right? And x minus alpha goes this way. Right? X minus alpha reduces, x alpha increases. Okay, so maybe in a second. Now, problem is I don't know anything about Q yet, right? The value of Q. So what I do is, given that it's a unitary representation, we can compute the possible ranges of Q. Okay, so what are possible values of Q? And then we can compare it with the list. Okay, so let us try to do it. So this is where some computation is needed. So let's take a vector from here. So take V0, capital V0, and compute. Then, well, so we know that x alpha V0, so the x alpha will increase, right? So V0 will go to V2. So it will go to a vector there, and it is non-zero, right? No, so x alpha and x minus alpha will not kill anything, right? Because we have the doubly infinite. Okay. So x alpha V0 is some V2. V2. Right? So let's compute the norm of V0. So V0 square. Because I know that we are starting from a unitary reducible representation. Okay, so this is simply the inner product of sorry, let's compute V2. Well, this will not be enough. Okay, that's why I'm computing this one. So I'll write down one more. So that is V2 inner product with V2. Okay. Which I will write as, so V2 is simply x alpha V. So x alpha V not inner product with x alpha V. Okay. Which is equal to the x alpha you bring to the left side, it becomes minus x minus alpha. Well, you have to prove that. That's not very difficult. In fact, you don't have to do any computation. X alpha you write in our real basis, those x1, y1, y2. These are complex matrices, right? Right in terms of the real algebra elements. The real algebra elements have to act like skew Hermitian matrices, right? Skew Hermitian operator, because group elements act like unitary, so the real algebra will have to go to skew. So skew Hermitian line, if I put it on the other line, I will get a minus sign. That is always given. So x alpha you write in terms of real ones, you will see that x alpha goes to this side as minus x minus alpha. So this would be simply x minus alpha, x alpha, v0, v0. So now you know why I did that, because I know what this is. And this we had computed. X minus alpha, x alpha to the L acting on Vn is something. Okay. So you apply that, you will see that this is nothing but minus 1 by 4 q minus 2 into 4. So remember that n minus 2l, n minus plus 2, so that is what comes. And now v naught square. Okay, so I will remind you that x minus alpha, x alpha to the L, Vn is 1 by 4 q minus n plus 12 into n plus 12 plus 2. So this is what we had to last class, x alpha L minus 1. So you apply that, you will get this. But you see, this is a positive number, right? This is the norm square of a vector. So this number has to be positive. This number has to be positive would mean that q is less than 8. Right? So you will get that, so implies q is less than 8. Okay? But that's not enough. Okay, so this is only one such condition. There are all these vectors, right? You write down all of them. So, but you don't have to write down all of them, because once you write down 3 or 4, you will understand what is happening. So,
n minus
minus 2, not plus 2.
I have an x minus alpha here. So n plus. If I had x alpha, x minus alpha, that would be okay. Well, otherwise I'll get q greater than something. So q less than something. Doesn't really matter. The range of q should be clear. That is all. So just to make sure that we are not missing out on any range of q, let us do one more such iteration. So instead of taking v2, we look at the norm of v0 and use x minus alpha to find out. So compute this way. So x minus alpha, sorry, x alpha v minus 2, x alpha v minus 2. Right? So the x alpha will take v minus 2 to v0, right? It increases. And then bring the in here. So I'll have a x minus alpha, x alpha v minus 2, v minus 2. And this again you can compute by r is a minus here. So you compute, you should get minus 4 into q minus 0 times norm v minus 2 square. So this implies q is less than 0. So here and here we had only q less than 8. So, and if you write down all the other conditions, you will see that q is less than 0. That's only you can write this in general. Take vn and vn plus 2 or vn and vn minus 2. Write it down. You will see that q less than 0 is equivalent to all the other things. That will. So now what do I have? I started with a unitary reducible representation. I have that q less than 0. Okay, and j pi I know is E1 and W. So all I have to do is to check whether it matches with one in the list, right? So I look at the principal series and the complementary series and realize that for any q less than 0, there is a representation. So the q values will match, and j pi is doubly infinite for the complementary principles. Which means by the theorem, the representation I started with is one of the principles. This is fine, and I can do that for all the cases.
Can you repeat this argument?
So the norm condition, because I know that the unitary representation, there is a norm around that, and the norm conditions tells me that the value of the Casimir has to be less than 0. This much is fine. So I have j pi, the k types to be even or even and doubly infinite, and the Casimir value less than 0. So I go to the list and check if there is something similar. Okay, so the pi lambdas I have and the principal series I have, they are the representations with doubly infinite even k types. Okay, of course, so that is something one has to do. Okay, that so one knows everything about those explicit things. Okay, so I didn't do any of those computations, right? So the principal series has all the k types, all the even k types. Pi lambda minus has all the odd types. Principal series has all the even types. And the q value for principal series is from 0 to 1 by 4 or something like that, and for the principal series from 1 by 4 to minus 1 by 4 to minus 1. Okay, this can be computed explicitly because you know the representation explicitly, you know the expressions explicitly for the Casimir explicitly, you just compute it. Okay, so that's a well-known expression. But the point is, for all the range we have got, so for all the range for Q, there is a representation there. So the infinitesimal data will match. Once the infinitesimal data matches, the representations have to be unitary. So when I start with the pi like this, it has to be one of the pi lambdas or the complement. Similarly for other representations. Okay, so this completes the classification of unitary reducibles of a set.
So in this one step somewhere, there you calculated norm of V2 and you got Q less than 8.
Yes.
Here you calculated norm of V0 and you get Q less than 0.
Yeah.
What's going on? I mean, this is
No, so there are infinitely many conditions. So I did just two of them, right? So only for V2 and V0. So you do this for all of them, and you will see that the common condition it's equivalent to saying Q is less than 0. So the Casimir's range is only from 0 to minus infinity. Those are the only possible values of Q.
if there is a V0.
Well, I started with that assumption, right? So the K types are even and double infinite. So all of them are there. All the V0, V2, everything is there. So if that is the infinitesimal data I have, I want to say it is one of the principal series or one of the complementary series. And the argument is this: I compute the Q value, get the condition for Q, and match with one of the existing representations.
This also calculates the norm of each of the VIs.
Yes. So see, the whole Hilbert space is determined by choosing vectors, orthonormal vectors from here, right? So if I take an arbitrary vector, if I know its norm, then that space is determined completely. There's nothing else there.
And the vector is canonically determined because
Using those operators, yeah, that is the easy thing. Yes.
so once you choose V minus 2, then it allows you to
Yeah, so once you choose anything from one of them, and then x alpha and x minus alpha fixes all of them. Okay, so that completes the puzzle.
So if you assume it's not doubly infinite, you can do
Yeah, it's the same. The argument is the same, right? So if it is not doubly infinite, let us say it is going from n to. So I know that it has to go from n to the right or n minus n to the left, one of them. Then I look at the Q value and then again.
So what would be the condition on Q then?
I don't remember exactly what the Q value.
the Casimir is always negative.
Yeah, so Casimir, so depending on how you define it, is either negative or positive, and there are certain restrictions for the eigenvalues.
So is it always like a semi-infinite interval or
Yes. So as Subhadra was saying, if it is positive, it will. So the way I define it is a negative operator. That is the negative less than. Otherwise, it will be zero.
no, like for other cases, starts at
No, in all cases, because it's see, Lie algebra has to act like skew Hermitian, right? So this is the square of such thing. It's either positive or negative depending on whether you put a minus or not. Okay, so I hope that satisfies everybody as far as the classification is concerned. Now we have Pranzel's theorem, but yeah, I am not sure I can do this in a coherent manner because there's quite a lot of computations involved. So some words first, and then I'll try to write down some. So there are two Cartan subalgebras, one coming from K and one coming from A. The A one is easier to deal with, and I am more familiar with that. Because if you look at K bi-invariant functions, that is the one which one uses. And the orbital integral corresponding to A gives me what is known as an Abel transform or Abel's integral equation. And that can be inverted. Okay, Lamb calls it freshman calculus. And it's not very difficult, but it's not too large. You have to do it. The one corresponding to K is a bit more complicated. It has certain discontinuities. But its derivative is a laticulus function and quite nice. So one expands that in the Fourier series, and the Fourier components or the Fourier coefficients are related to the discrete series characters. Then one puts together all these and then inverts these transforms. You get the inversion. So it's quite involved. Even for a SL2R, it's not a completely easy. So I'll still some time I'll try to do the K bi-invariant case, which is easy. Okay? So I'll write down some integral equations and invert them. Okay? So some computation. But I'll tell you a few things before that. How one computes the trace and things like that. So in particular, so if you remember Devendra's first lecture, you saw three terms. One was a series that corresponded to the discrete series. Then there was the lambda tan hyperbolic pi lambda by 2 as one part of the Planck measure, and there was the lambda chord hyperbolic lambda by 2. That was the other part. Okay. So we'll see only the one part which has the tan hyperbolic. That is what corresponds to the K invariant functions. Okay, because that comes from the what is known as the spherical principal series. And the functions we are considering, since they have certain symmetry, they don't survive on other representations. So if pi, so this is something which you have been hearing for a while now. If pi is a unitary reducible representation of G, there exists a function theta pi. So initially a distribution, but then it becomes a function, which is called the character of pi, right? So if I take a nice function, C C infinity, T, then pi of psi. So remember, this is the Fourier transform of the function psi. So this is the G fx ix dx. This is a priori the boundary operator on the Hilbert space where pi is realized. Right? It's a trace class operator. Yes. Okay, sorry. So I used pi f, right? So, right.
Sorry, I can't read that.
Huh?
Psi of pi of
Pi psi, so pi f is trace class. And the inversion formula reads, so maybe I will, so I need all the notation again. So for n greater than or equal to 2, let theta n be the character of dn plus direct sum dn minus. So you put it together so that you have a nice expression. So that takes care of all the discrete series to start with for n greater than or equal to 2. N equal to 1 does not come as a discrete series. Okay, it's not a discrete summand of L to G. It is part of, remember, the pi 0 minus. It decomposes into two things. So it is part of the continuous Planck measure. Right? That's the chord hyperbolic part. For sigma in head, so m is just plus or minus identity centralized for A in K. This has only two representations, so one was trivial and the other one which I call fine representation or something, right? The theta lambda sigma. Okay. Be the corresponding character. Be the character principal series. Principal series pi lambda sigma. Okay, so pi lambda sigma, and sigma is trivial. This is just pi lambda, and sigma sign, then we call it pi lambda minus. Okay, so that was our notation. Then one can write down the so complementary series does not contribute to the branch formula. Maybe a notation here so that I don't have to keep writing trace. Theta pi. So theta pi is the character, right, which is actually a function. So theta pi acting on a function psi is simply the trace of psi pi. Sorry, pi psi. Yeah, right. So the principal formula is the following. So this is what we had seen in the first lecture. For every so the I should say something about all the constants of theory. So this is just copied from lab or on another node. So the constants may differ depending on what parameterization you use and so on. 2 pi f e equal to summation n equal to 2 to infinity n minus 1 theta and f. So theta and f is just the trace of pi f, where pi is, so remember theta and is the character of these two representations, the sum of these two representations, right? So that takes care of the discrete series part, plus 1 by 4 integral over r theta. Now comes the principal series ones. So pi lambda, theta lambda, so that is the character for pi lambda, and C function of the Rishchandra, so that is lambda parabolic pi lambda by 2 d lambda. So this corresponds to the spherical function theory, that means functions which are k by invariant. That is the only thing that will come. And this particular quantity here is called the spherical Fourier transform of f, plus the other principal series, which gives me integral over r theta lambda minus, so that corresponds to these representations, the other set of principal series f, and I have the lambda convex pi lambda by 2. Okay, so these two are well, the Rishchandra C functions. So that is how the inversion formula will look like. Okay? So I'll just tell you how this part can be obtained. Is that okay? Or do you want me to stop? Okay, just few steps, and if you think it is getting too much of calculation, you can stop. But one knows the characters. Okay, so I should tell you that as well. So theta pi is the character of pi. These are functions. Okay, these are functions which are explicitly computed. You can write down what they are.
Lecture was that this theta n, in fact, it takes care of both dn and d minus n.
Yes. So theta n is the character of the direct sum of both the representations. Okay, so it's not just the dn that appears. Dn minus 1 also. Complementary series does not. And I think what you were saying about n equal to 1 is that at n equal to 1 you have the d1 and d1 minus, that goes with pi 0 minus, so that is here. But it's not a discrete sum because it's not square integrable.
It is missing.
Yeah?
It is missing.
Well, it is. I mean, it is part of the continuous vector. I won't say it's missing. It doesn't appear as a discrete sum. I mean, it is not supposed to appear as a discrete sum because it's not a square integrable. All right. So I'll try to do the Fourier inversion with modulo sum proof for which gives me this part. So,
I'm certainly happy to know what is the role of that and
so that is the principal element set, right? So that will pop up when we invert the class. So Fourier inversion for CC infinity. So this is the k by invariant. Okay, so this means f of a1x a2 equal to f of x, right? So it's in particular it's conjugation invariant. And so this survives only on A. And remember the K decomposition. So the K in the first part and the last part doesn't do anything. So it's a while group invariant function on A. So think of it as a even function on the real line for our practical purposes. So first the marks is, or first step or phi f is 0 if phi has no k fixed vector. So that rules out lots of representations to start. Okay, that is why the k by invariant case is a bit easy. Well, why is that? That is easy to see. So phi f is an operator. This is f of x, phi x, dx. Now f has a lot of symmetry, right? So f is invariant with respect to the k action on the right. So I can put a let's say k inverse here. Nothing changes, right? And dx is invariant under whatever you want to do. So k inverse goes to this side as k. That's fine. But pi x k is pi x times pi k, and the pi k can put outside. Right? So now this guy is independent of k, so I can integrate with respect to k, dk. This is the projection to the k fixed vectors. Right? Remember the projections En we defined. En was e to the minus in theta pi k theta d theta. The n is 0 here. Right? So this is just E0. E0 is the projection onto the k fixed vectors. So if f has this right k invariant property, phi f will be 0 if the representation space does not have any k fixed vectors. So now in our list, the only ones with fixed vectors, meaning the V0 has to come. V0 comes only for the principal series by lambda. Right? Complementary series does not even appear in the principal. Only by lambda is there. So we need to compute only pi lambda of f. Right? And trace of that and then write down the inversion. Fine? Okay, so that's one step. Here. Okay, I should say lambda in the real line. Right? So in the list, lambda is always in the real line. Okay, that's it.
Is there a relation of that lambda with the n that you've chosen? N to be greater than equal to?
No, this is for the discrete series. Lambda and n are independent. So discrete series is discretely parameterized, dn's. The continuous part consists of principal series and the complementary series. The principal series is parameterized by, well, depending on how you write lambda is either real line or purely imaginary. So again, depends on the book you look at.
Sir,
Yeah.
that can you please repeat that argument that why you should have a k fixed vector?
So f has right k invariant property.
Yeah.
Right, whatever k I put, that disappears. So the operator pi f is f of x. Okay, so I'll write these things again. Fx pi x dx. So I can put any k here I want, right?
Yeah.
Let's put k inverse so that
Yeah.
it doesn't change anything.
Yeah.
But the k inverse goes to this side as k after a change of variable,
Yeah.
right? And so this is a homomorphism, it becomes a product pi x pi k. So I'll have a pi k outside. Right? So I can write this as pi x dx times pi k. Or any k I want.
Yeah.
So, but this part is independent of k. So I can integrate with respect to k.
Yeah.
And this is my E0, the projection to the k fixed vectors.
Yes. Yeah.
So if there are no k fixed vectors, this projection is 0.
Ah.
So pi f is 0. So which means that if I take a function which has right k invariant property, it will survive only on the first set of principal series. All the other pi f's are 0. Okay. Now, well, we'll compute the trace of, so it's a trace class operator, pi lambda phi, right? So if f is a part f, CC infinity, right? Then pi lambda f is a trace class operator. I want to compute its trace, this operator's trace. So think of a matrix. How do you compute the trace? You simply add the diagonal elements. Let's just add the diagonal elements, right? Only thing is we are on a infinite dimensional Hilbert space, so that's an infinite sum. But what happens is because f comes from this space, only one term survives. So that tells me what the trace is, and that's what the spherical Fourier transform of f. Okay. So how do we? So let's write pi lambda f. So where is pi lambda realized? So this is where explicit things matter. So pi lambda is a operator from L2 of even functions on k. K is just a circle, right? To L2 of even functions on k. Right? Remember the k types. K types are v0, v2, v minus 2, etc. Think of them as even functions on the circle. And there is an expression for it. Okay, you have a direct explicit expression for how pi lambda g acts on L2 of the circle with even functions. You can write down. But in particular, I can choose the basis to be 1, e to the I2 theta, e to the I4 theta, e to the minus I2 theta, and so on. And the exponentials. And now, when I compute the trace, so what is the trace of this? So trace of pi lambda of f is, well, pi lambda of f, you choose that orthonormal basis En, right? So you apply it on En, you take inner product with En and sum it up. Right? This is the trace. Okay. Not get into the computation, but at least let me compute the trace and then tell you what it is, and then perhaps write down 2 lines and then stop. So how do I compute pi lambda of f acting on En? So En are n even and exponential, right? We are on the circle loop. So this is a simple computation if you know how to write down this. Right? So this is simply f of x, pi lambda of x, right? That is the operator acting on En in a product with En. Right? Now we can do whatever we want. Remember, it survives only on the k fixed vector, right? Because of that k invariant. So only the term with 1 1 will survive. Everything else will be 0. Right?
0, 0. You said 1, 1.
Well, 1 1 meaning the constant function 1 1. Right? So E0 is 0. Yeah, correct. Right. So this is 0 if n not equal to 0. Otherwise, it is integral of f of x pi lambda x acting on the constant function 1 in the product with the constant. This, you notice, is a k by invariant function. I put a k here, 1 doesn't change anything. If I put a k here, it comes out as pi lambda k, comes to this side as pi lambda k inverse, and 1 is fixed again. So it's a k by invariant function. Okay, so this is called the spherical function, p lambda, and this is called the spherical Fourier transform. So the trace is simply the spherical Fourier transform of the k by invariant function. Okay. So the inversion formula when you write down, so I didn't get into the other transform, but let's write down the inversion formula. So this would be some constant integrated over r by lambda. So what is the by lambda? That is the trace of f lambda. Okay, so this is denoted by f by lambda. Just like the usual Euclidean Fourier transform, you are integrating f against phi lambda, which is what is called a spherical function. These are actually eigenfunctions of k invariant differential operators on G by K. Just like the exponentials in the case of I. So f lambda and well, mod c lambda to the minus 2 d lambda. This is how the inversion would look like. The mod c lambda to the minus 2 is the C function, which turns out to be lambda times f2 over lambda by 2 after computation. Okay. Now,
So there are two many functions. There is phi lambda and now there is c lambda.
the phi lambda, so phi lambda is the trace, right? So f integrated against phi lambda will be the trace. So I'm integrating out the variable x, so it's a function of lambda which I call f hat lambda. That is the Fourier transform. Right? Inverting gives me this. But now this is not the inversion, the proof. So, okay, 2-3 lines. This object is the Euclidean Fourier transform of the Abel transform. Okay, so f is a k bi-invariant function, so it's a w invariant function of k, and on A you can define this integral transform. That is the orbital integral. That gives me what is known as the Abel transform of A. And then, so that's a function again on A, which is a w, so it's an even function on A. You take the Euclidean Fourier transform of that. That is this object. Okay. And the Abel transform, so that is a transform. So forget about all the groups and so on. I have a function on the LN, I have a transform. I get another function. Okay, I invert that. The Abel inversion gives me the original function. So the Abel inversion is done via an integration and a differentiation. So it's an integral differential operator. Okay? And then you write down the abstract inversion formula involving trace and so on. This is what will come out. So I'm sorry that it is too big, but it will take another 15 minutes to write down. I stop.